now that I scared you enough with quantum mechanics, we are going to start applying it, and I promise you the applications is going to make a whole lot more sense, okay? We have seen that the energy of atomic orbitals increases as the principal quantum number increases, okay? Obviously, as n increases, the orbital becomes bigger because it's an outside layer. You're getting to bigger and bigger layers, so the electrons spend more time farther from the nucleus. The farther they are from the nucleus, the weaker the attraction. These are electrostatic attractions. Electrostatic attractions depends on the charges and is inversely proportional to the distance squared. So the bigger the distance, the weaker the attraction, so the less stable that situation is. Okay? Now, some cases, and Halloween is a very good example, you only have one electron. So you can say all the energy is always the same. You're going to find every so often that you have orbitals that have the same energy. Okay? And we call those degenerate energy levels. That means they have the same energy. And this will come up later on, but that's all it means. Okay? Now, when you get beyond hydrogen and you have two or more electrons, you're going to have to consider, one, the attraction of the nucleus. The protons in the nucleus are going to attract the electrons, but the electrons are going to repel each other. Okay? So you have two sets of forces in there that are competing with each other. In general, you can see that an s orbital has lower energy than a p less than a d less than an f. But that's where, again, the interaction between electrons is going to affect that. Okay? And we're going to start putting electrons always beginning with the lowest energy level first. So experimentally, everything looks good. 1 is lower than 2, 2 lower than 3, 3 is lower than, that's fine. S is lower than P. Everything looks real good. And then all of a sudden say, wait a moment. You're saying that the 4S has a lower energy than the 3D? But I thought 3 was supposed to be lower energy. Well, experimentally, that's what it is. And the 5S is lower than the 4D. Like I said, this is all an effect on the interaction between electrons. And I don't want you to panic. When I took chemistry, I know my professor said, memorize them. You've got to be kidding. Memorize them? I can't memorize this. I did come up with a little trick that helped me. The trick is too complicated. I tried to use it with my students. Never mind, forget it. So I'm not going to waste time. I'm going to show you an easy way that I have given anything when I was an undergraduate to determine the order of the orbitals. But I want you to know that they don't follow the 1, 2, 3 SPDF perfect because of the interactions between electrons. And that's going to make things confusing. Now, we'll get to that in a minute, okay? How to know the order. But the ratio of electrons is called the electron configuration. And we represent it by giving 3 pieces of information. We have to put a number for the principal quantum number. So that 1 here tells you that n equals 1. Then a letter to determine the orbital type. So that S tells you that's an S orbital. This is why it's easy to use letters, because you have so many numbers that would be very difficult. By alternating letters and numbers, it makes it a bit easier. And then a superscript that tells you how many electrons. In the case of hydrogen, we have only 1 electron. So we have 1 electron in an S orbital in energy level number 1. Let me get the periodic table. We can look, for instance, carbon. To make something, carbon has 6 electrons. So you fill the 1s, so you move to 2s, you can put 2. That has only 2 electrons. So now you move to the 2p, that'll be the next one. And we have used 4, we said carbon has 6, so it's going to be 2p2. That is the electron configuration of carbon. We have them in order, and we start filling with the lowest energy, and we fill up until we use up all of the electrons. Okay? Again, the number in front tells you the energy level, the less S tells you the orbital type, and the superscript tells you how many electrons in that particular orbital. So make sure that the number of electrons you use equals the atomic number in there. And we are going to be filling, like I say, in order, beginning with the lowest energy, and that's called the Aufbau principle. Beginning with the lowest energy and being going up. And remember, don't forget the Pauli exclusion principle. You cannot have two electrons with the same for quantum numbers. So the question is, what do you do? Do you memorize the order of the orbitals? Believe me, you don't want to do that. Been there, done that, you don't want to do it. If you have a periodic table, it takes care of that. Because you're going to learn that this group in here, I call it usually the towers, but this is going to be the S block, meaning that we are filling S orbitals. In pink, we have the P block because we are filling P orbitals. The transition measures in here, we are just going to call it the D block because it's filling the orbitals, and this is going to be the F block. And all you have to do is go in order from top to bottom, left to right. So you have 1s1, 1s2, 2s1, 2s2. What is next? 2p1, 2p2, 2p3, 2p4. Move on. 3s1, 3s2. So let's say that I want the configuration of iron. I start from the beginning and say, okay, you fill the 1s orbital, 1s2. I fill the 2s, 2s2. I fill the 2p, 2p, 6, 1, 2, 3, 4, 5, 6. I fill 3s, 2. I fill the 3p, 4s2. Now notice when we get to D that you go from 4 to 3. That's the only thing you need to remember. Okay? This part of the table seems to be sunk. So that's how I remind myself that you have to go down one principal quantum number. Yes, so you go from 4 to 3D. How many? Where is iron? 1, 2, 3, 4, 5, 6. 3d6. You see? I didn't have to memorize that the 4s come before the 3d6. I just went through the periodic table, like I said, from left to right, just like you're reading. How do you read this? You read from left to right, and when you finish a line, you move to the next line. You do exactly the same thing. If you have a periodic table, you can write an electron configuration with no memory. The only thing to memorize, when you move from S to D, you go down one number. When you move from D to P, notice the periodic table goes up again, so you go up one number. If this is 3D, this is 4P. That's the only thing that you need to memorize. When you get to the F, I doubt you have to use it, but it's going to go down one more number or go up one more number. But if you remember that, the periodic table will give you the electron configuration. Believe me, I have given my car when I was an undergraduate if someone had told me that. It's amazing because when I got my master's in chemistry, they still did not explain this. It hasn't been that long, for Pete's sake. I didn't learn this until I had graduated with my PhD. I was teaching an officer in a general chemistry book. I thought, this is easy. Why didn't someone show me that before? I couldn't believe it. Okay? That's why I'm not showing you any of the tricks. Especially if you look at high school books, they have all sorts of tricks to be able to do this. And if you're really neat and very, very careful, they work. But if you have a wonderful memory, they work. This is easy. Anybody can do it. A caveman can do it. That's why I tell students, you always want to have a periodic table with you. You may want to ask your instructor, but my students are always allowed to have a periodic table with them in an exam. Because the periodic table is your best friend. It will solve so many of your problems. And I figured that out when I was getting my masters, any lab that you went had a periodic table. Why? Because it's so useful. It wasn't there for decoration. It was there to be used. High school teachers who make students memorize part of the periodic table. That's ridiculous. Print it out. And one of the things that I make available to my students is a big copy of this one. You can print it out, put it on a sheet protector, and just carry it with you. Carry it everywhere. Whenever you're listening to the videos, have your periodic table. Whenever you're doing homework, have your periodic table. Whenever you're taking an exam, if the instructor agrees, have the periodic table. Why you memorize things that the periodic table will give to you? Doesn't make any sense. Now, another way to represent orbitals, electrons will be the orbital diagrams. That's more like pictures. Okay? So, supposedly what you're doing is showing the individual orbitals and show the arrangement of electrons. Now, to tell you the truth, I don't know anybody who wasted the time putting squares. Most of the time, just put a line, and they know what it means. An up arrow means that you have a plus 1/2 spin quantum number downwards minus 1/2. So every line could have up to 2 electrons in there. Helium has 2 electrons, so you put them in there. Lithium is 1s2, 2s1, so you put 2 electrons, and now when 1s is full, then you can move to s. Everything is fine. You just keep adding electrons. Remember, there's 3 p orbitals, the x, the y, and the z. So far, everything makes a lot of sense. The problem is when you start moving to the next one. Okay, I've had students, 1s, 2s, 1, 2, 3, 2 p's, and they put 2 electrons in the same. No. Okay? Hund's rule. Okay? By the way, these are degenerate. Whenever you're talking about degenerate orbitals, meaning they have the same energy, you try to have the maximum number of ampere electrons. Meaning, if there's 3 spaces, you start putting ampere electrons. And only when all 3 spaces are filled, then you can start pairing electrons, because the ampere electrons are more stable. Okay? 2 things that I always tell my students to watch out. You have people run a long thing like that, and they call it 2p, and then they start putting like this. No. There's 3 2p orbitals. If you want to draw 3 squares, fine, because you can see that there's 3 orbitals. If you're going to use a line, use 3 lines. So you know that there's 3 separate orbitals. Your choice, 3 squares, 3 orbitals, 3 lines, but no one long line. Also, some students like to do that. And they say, oh, that's 2 arrows, one upwards, one downwards. Well, that's what you say. But actually, this has 3 lines. This is meaningless. Okay? So, I count this wrong, I count this wrong. If you want to represent that one, you do it like that, or you put the 2p, 3 lines, 1, 1. If it's one that you have pairs, make sure you put 2 arrows. Don't put any weird symbol. Okay? Very, very easy. Main problem my students have, I ask in the exam, give me the electron configuration, and they start drawing lines. Give me the atomic orbital diagram, and they start writing 1s, 2 1s, 2 2s, 2. This is the electron configuration. This is the orbital diagram. Read the question. Answer what they ask you, know what you're thinking about. Okay? Be very, very careful, because there are 2 different ways of representing the electron. And quite honestly, if I ask you for the electron configuration and you give me the orbital diagram, it may be right, but you don't get no credit, because that's not what I ask you. Answer what they ask you, not what you think they're asking you. Okay? So here you have examples. The first 3 electrons, each one in a different orbital, then you start doubling until they fill up. It's very obvious. The outermost shell, the one that has the highest value of n, The electrons in there are called the valence electrons. Okay, the ones underneath, they're going to be core electrons. What is this important? Because the valence electrons are the ones that are involved in chemical bonds and reactions. They're the only ones that do anything. Okay? Now, you know that we field begin with the lowest energy level. So these core electrons, they're kind of occupying the base. Okay? They're holding everything in place. But the valence electrons are the ones that we're going to be worried about the whole semester. Okay? The core electrons always are a noble gas configuration. Why? A noble gas is an element that has the outermost shell full. So the core electrons are always full, because if that outermost shell was not full, you couldn't move to the next shell, that would be the valence electrons. Okay? Now, differentiating valence and core electrons help you a little bit, because we have abbreviated electron configurations. You can put the noble gas that matches the core electrons. You have to put it between, not in parentheses, brackets, and then you only take the time to write the valence electrons. Let me show you an example. Sodium. The electron configuration is 1s2, 2s2, 2p6, 3s1. So in pink, they're showing you the core electrons. There's only one valence electron. You can go to a periodic table and say, oh, that's the electron configuration of helium. So you can, or neon, sorry. So you can put neon between brackets 3s1. Don't forget the brackets, because if you put neon, then it's meaningless, okay? Brackets say electron configuration of neon. It's just an abbreviation. You don't have to write the whole thing. You can say, well, it doesn't help that much. Wait until you get into bigger atoms, and then all of a sudden, you can have an electron configuration that takes 2 lines in your paper to fill in. Or you can write the abbreviated that's just as short as this one. It may help you avoid making mistakes, because wherever the order of the orbitals is, it's not what you expect, it's not the predicted. Remember, we talk about that. Sometimes you can have an N3 that has a higher energy than the N4. If you combine them as electron configuration of a noble gas, you don't have to worry about making a mistake. Okay? So abbreviated electron configurations are very helpful. It helps you focus only on what matters most, the valence electrons. But once again, when you're taking an exam, be very careful. What do they ask you? Do they ask you for the electron configuration? That means the whole thing. 1s2, 2s2, 2p6, 3s2, blah, blah, blah. Abbreviated, noble gas configuration, and the valence electrons, or the orbital diagram. Again, answer what they ask you. I do have a very long worksheet where I ask you to write all 3 or all of them, so you don't confuse them. But it doesn't do any good if you don't read the questions. You understand that? Another advantage of abbreviated configurations is that you can compare groups. Look, in group number 1, they all have S1. It's a different energy level, but they all end up in S1. Group number 2, they all end up in S2. And you can see in all of the groups. That similarity in electron configurations is going to become very important, because we're going to see that all of the elements in one group have very similar properties. No wonder. They have one valence electron, they have the same number of valence electrons. Of course, they're going to have similar properties. So abbreviated electron configurations remind you of that and allows you to see it very easily. Now, when you get into transition methods, it's going to be a little bit more of a pain, because you're adding 3D, and remember the 3D comes after 4S. But if you remember that when you move into the transition methods, you go down one value of n, and then when you move back into the non-metals, you go up again. It's no big deal. We knew that there is 5 d orbitals, so that means you can have 10 electrons in there. And after you fill the 3d, then you move to 4p. You go from 4s down to 3d, and then when you go to p, you go up 4p. That's what I told you. Remember, when you get to transition metals, go down and then go up when you get out of them. Okay? In the transition metals, you have the F subshell, so you have 7 different orbitals, so 14 electrons. Once again, when you move from the D to the F, go down one more. When you move from the F to the D, go up one more. Okay? I don't know if you'll ever get to use them, seriously. And there's some exceptions. Okay? You're going to see that's very common in chemistry. Copper and chromium. They're not going to follow the order that you expect from the periodic table. Okay, so for copper, you expect argon 4s2 3d9, but it's actually 4s1 3d10. Who have guessed that? Chromium should be argon 4s2 3d4, but it's 4s1 3d5. There's an explanation for that. Every time you have either half filled or fully filled D subshell, it's very stable. Okay? The same thing actually applies, we'll see later on, to S orbitals. So this one has the S full and the D partially, not half. When I mean half, when I say half, I mean half. So that's not very stable. This one has S half full and D is full. So we eliminate the partially full. That's why this one is more stable. The same thing in here, you have S is full, D is partially full. In this one, S is half full, D is not full, but it's half full. Half is better than partially. So once again, we get rid of the partially full, this one is more stable. Okay? So that is the only exception. When you have a choice between a partially full cell or a cell that is either completely full or exactly half full, the exactly or half full is better than the partial. Partial is the most unstable. Okay? Now, what do we do with ions? Well, remember, an ion is an electron that's going to gain or lose electrons. It's an atom that gains or lose electrons. So a cation means that you lose electrons. The key is which electrons do you remove? Main group elements, meaning you're filling the S or the p orbitals, the last added are the first out. Kind of like in a job, the last person hired, the first person release. If you're talking about transition metals, the d orbitals cause a lot of trouble. We are going to be hearing that. So yes, you lose the ns electrons, but once the ns electrons are lost, you're going to lose the n-1 ds, or maybe even -2. So you're not going to necessarily be in order. When you go to an electron configuration, you'll see that you lose these electrons and then the ds, and sometimes they won't even follow this. This is the general rule, but remember that transition metals. So whenever they want to break the rule, they do it and they don't care. Wait until we talk about elements, metals that can form more than one ions. We are going to say, oh, they should have lost these electrons, but they chose to lose only one and then they start losing these. Why? Because they felt like it. And nobody can stop them. Okay? On the other hand, an anion means that you gain electrons, so you just follow the Aufbau principle. Just keep adding them in order of energy, so that's easy. So let's look at a few examples. Okay, I have a number of ions in here. What we're going to do is a little bit more time consuming, but avoids errors. I always write down the electron configuration of the atom, and then add or remove electrons depending whatever the ion is. So we look at sodium. Sodium is 1s2, 2s2, 2p6, 3s1. How do I know? I'm using the periodic table. I did that. Okay? So it loses one electron. It's going to lose the 3s1. That's the valence electron. So that's the configuration of sodium plus 1. You have the configuration of phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3, because that's what you run out of electrons. Now it's going to gain 3 electrons. Aufbau principle says we are going to add into the 3p orbital, because there's empty space, that's the lowest energy available. So you have 3p6. Aluminum, it's at 3p1. So because it's not a transition metal, but it's already close in the transition metals, it's going to lose S and P's. Okay? It loses, they're telling you it was going to be aluminum plus 3. So yes, you lose all 3 of them. So you stop at 2p6. Iron, transition metal. So it depends. They give you iron plus 2, and iron plus 2 is going to lose the S first. So it goes from 3p6 to 3d6. But you will find out in the next chapter, iron could decide to lose 3. And then it's going to lose the next from the d orbital. But notice that the s orbital is lowest energy, but it loses those electrons before it loses a d. So you have to be careful with the transition metals, okay? Samarium, same thing, it's going to be plus 3, so you begin losing from the 6s. But that's only 2 electrons. You want to lose 3 because it's plus 3. So the next one is going to be from the 4f, and then for 4f plus 5. So remember, with transition, in a transition, you lose the S, and then you continue with either the D or the F that actually have higher energy. But you lose the S electrons first, even though they're not the highest energy. Okay? That's transition metals for you. So once again, do you want to practice? I have worksheets where you write electron configurations, abbreviated electron configurations, and orbital diagrams for atoms, ions, every possibility. So if you want to practice it before you have an exam, so you make all of the mistakes you're going to make while it doesn't count, go to a video description, make an appointment with me through Wisant, and I will give you those worksheets, and we can work together and make sure that when you take the exam, you know it real good.